afternoon, everyone, and welcome to our presentation on age and distance to an open cluster. I am Aminatou, and I'm thrilled to have you here today. This project has been a collaborative effort, and I'm proud to introduce my dedicated team members who have contributed significantly to our research.
Hi, my name is Saksham Agarwal, and I attend Walnut Grove High School.
Hi, my name is Abhay Bhaskar, and I attend the Edison Academy Magnet School.
Hi, my name is Derek Chang, and I go to Round Rock High School.
Hi, my name is Khedaar Kashyap, and I attend Leland High School.
Hi, my name is Aminatou Seye, and I attend Mara High School.
Hi, my name is Aayush Tripathy, and I attend Hillsborough High School.
Hi, my name is Sriya Veluri, and I attend South Brunswick High School.
Before we begin, I would also like to have a huge thanks to our mentor, Dr. Kuper, who has been an invaluable guide providing us with expert insight and support. Now, let's delve into the background information about open clusters. So, what are open clusters? These are a group of stars that are loosely held together by gravity and were born from the same cloud of gas and dust in space, which is known as a molecular cloud. The size ranges from a few dozen to a few thousand stars. Over time, the stars in the open cluster slowly move towards each other and may disperse after a few million years. These clusters are important in astronomy because they give us a chance to see stars in different sizes and stages of life, all at the same age and made from the same material. Also, because the stars in the open cluster are similar in age and chemical composition, astronomers can use them to check models of cellular evolution and ages of stars. Characteristics of open clusters. Stars in open clusters are primarily held together by mutual gravity within the system. As noted before, this leads to relatively weak gravity, and as a result, most stars in the system will disperse after a few 100 million years. Open clusters have both young and old stars, but because of the weak gravity, the stars typically are less than 1 billion years old. Since open clusters are relatively young compared to globular clusters, they consist largely of blue stars, which are associated with higher temperatures. Stars in the open clusters are also typically in the main sequence of a Hertzsprung-Russell diagram, which is shown here to the right.
So now diving into the open cluster that we examined in this project, it was NGC 4815, which is an open cluster in the Musca constellation. And this open cluster can be viewed from the southern hemisphere if you're using powerful binoculars or a telescope. And one of the most important things about this cluster is the fact that there's not been a lot of recent research into it. In fact, the most recent study into this open cluster was almost 3 decades ago. And since then, obviously, there have been major leaps and advances in the data available and also the technology that we could use as a team. And this allowed us to get a more accurate information about the age and distance of this open cluster. So the telescope that this data came from was from the Southeastern Association for Research in Astronomy's telescope in Cerro Tololo, Chile. So you can actually see in 2 of the images, one of which is actually on this mountain in Chile, and the other shows a little bit more of the inner workings of the telescope. And then furthest to the left, you can see an image of the actual open cluster. But actually just diving into a little bit about the problems that the telescope faces. One of the main ones is the fact that there's a lot of gas and dust that can obscure the open cluster from the view of the telescope. And we'll actually discuss a little bit later about how we accounted for this and attempted to mitigate it. Also, high humidity and precipitation can lead to water vapor forming on the lens, which can cloud the view that it gives of the open cluster. And also a balance between getting a bright enough image and a sharper image, because as there's a narrower aperture of the telescope, the resolution of the image will increase because less light is able to enter. So there's also less blurring because of light diffraction. But the problem that arises because of this is that since less light is entering, sometimes the image might have an artificially low amount of light. So it's really this balance between 2 factors that have to be managed with telescopes.
Now that we've set the goals and the context for our situation, let's understand what's the key important concept to finding more about the open cluster, and that's through photometry. Photometry is the measurement of the brightness of stars in the pictures, essentially looking at pixels and trying to calculate how bright they are so we can learn more about the stars. We have to apply a concept called filters. For instance, if I put a blue filter over a large amount of stars and they tend to be in the red star range, it's going to come out very dim. But if I change the filter towards a red filter against the red stars, it's going to be a lot brighter. And shown in the ResearchGate image, we can see that based on the filters, you're going to see different kinds of brightness for different types of stars. Because we're mainly targeting hot and young stars, as explained before, you're going to use the blue and greener visual filters to see NGC 4815. And finally, the last niche part is our calibration. As we're using not only flat and dark files, we're also going to be using many different flat calibration files that can make it very easy to understand and also get the best measurement for the flux and brightness. But to go from here, when we're analyzing the region of sky, it wouldn't be efficient for just one of us to look and do the photometry for the whole section. So instead, we split NGC 4815 into 7 key regions and did analysis for over 257 stars out of the 8,500. We used the software of AstroImage-J with the calibrated B and B filters, and we targeted the stars for their magnitude and calculated the B minus V value, which can help us understand its color index. This is our B minus V collected data.
So after we had collected the photometry data, we classified all 257 stars in the open cluster according to their spectral type. Stars are classified mainly in 5 ways, which are surface temperature, luminosity, chemical composition, mass, size, and age. Based on these factors, the spectral type of the star is identified. The spectral types are O, B, A, F, G, K, and M, where O has the highest luminosity and M has the lowest. This classification of stars can be summed up into the Hertzsprung-Russell diagram, which measures a star's luminosity in relation to temperature, spectral class, or color. The HR diagram is important when astronomers are charting the lifestyle of a star, and it helps classify stars by spectral class in open clusters. In our study, we measured the stars' B minus V values indicating their color magnitude. And using this magnitude, we checked which color indices it was in between, given a reference sheet, and we could easily classify the stars. Additionally, the main sequence stars are the stars that show up on the diagonal line of the HR diagram, and they represent the majority of the stars in the universe. And this is called the main sequence, where the stars spend most of their lives. Also, what's important to know is the zero-age main sequence, also known as the ZAMS line, which is the time when a star first joins the main sequence on the HR diagram. And this helps us to identify the age of an open star cluster.
From our analysis of the photometry, we found that there were predominantly B stars in NGC 4815, but due to the lack of finding no O stars in the cluster, we estimate that it is at least over 10 million years. And despite being in a very hot cluster, we were also able to find 2 M stars, which are incredibly dim when compared to the B or A stars. We also got a good sample of the sample G type stars, which is just like our sun.
So over here on this graph, you can take a look at our initial color magnitude diagram. And as you can see, our ZAMS line is very far away from our initial recordings of our stars. And this is largely due to a phenomena called reddening. And what reddening is it's a phenomena that occurs when starlight appears more red due to the scattering of light. To further explain this, we can take a look at this diagram on the right, where a distant object will produce blue and red light. And since blue light has shorter wavelengths, it is more prone to scattering from dust and other space material, whereas red light can get through it much easier. As a result, starlight will appear more red to an observer, where in reality, it is actually consisting of more blue. So to do this, we have a reddening value, and our image of NGC 4815 had a reddening value of 0.808. And it is important to note that this is actually it's a relatively high reddening value. And so in order to correct for reddening, we use 2 formulas that are shown on the below. On the left, we have our true color index, which is our B minus V. And then on the right, we have our magnitude, which is our V filter.
So as previously mentioned, we had to correct each star's V and B minus V value for reddening due to the fact that there was an abundance of space dust which can scatter the light emitted from each star. By correcting the V and B minus V values, this gives us our true color index and our magnitude for each star. And as a result of the correcting, we ended up finding that the stars present in NGC 4815 had a very similar color index. Through our photometry, we noticed that this open cluster consisted of primarily young and bright B-class stars. And initially, this wasn't exactly what we expected because there wasn't that many stars that deviated from the data trend. So what we decided to do was to perform additional photometry on other faint and bright stars that were present in the cluster. And we still noticed that that NGC 4815 primarily consisted of B-class stars, and this led us to believe that NGC 4815 is a relatively young cluster with a lot of space dust in between, which would make sense, which would make sense because there aren't that many old and faint stars present.
And so what does all this data and analysis tell us? Well, by using the B minus V corrected value and the corrected V magnitude of our reference star, we are able to use the distance modulus equation as shown above to get an estimate of the distance of NGC 4815 from Earth. However, since we did not know the absolute magnitude of any star, we use the absolute magnitude of the Sun for the capital M value and use stars similar to the Sun, or class G stars, for the lowercase m value. But when we use the two stars with the closest corrected B minus V value to the Sun, we got two very different estimated distances, as you can see in the second bullet point. To combat this, we decided to estimate the distance by taking the mean of the estimation across all class G stars. And by doing this method, we were able to get an estimate that NGC 4015 is approximately 426 parsecs away from Earth. And what about the age of NGC 4015? And so first we have to talk about a turnoff point. And a turnoff point of a cluster is when the majority of the stars in the cluster begin to deviate from the main sequence relative to the Zam's line as shown in the graph below. This point is used to determine the cluster's age, as the cluster cannot be older than its oldest member star. Since the turnoff point is about B minus V is approximately 0.1, this implies that the oldest member stars have a B minus V of 0.1, which classifies them as an A-class star. This in turn indicates that NGC 4015 is about the age of an A-class star, or about 400 million years old. And please note that all V corrected values were shifted down by 8 units to correlate with the Zam's line.
From this project, our most important takeaways were how to use photometry on a telescope image to find the age and distance of open star clusters, and to contribute to furthering research about stars, and especially provide newer data about open cluster NGC 4815. As 2024 Seye's interns, our highlights of the program were collaborating as a group and forming new connections, having subject matter expert Olivia Kuper as our mentor, learning how to use software applications like AstroImageJ, Google Sheets, and Excel, and taking away key research skills and workplace experience. Some of our challenges were trying to overlay our Zam's line onto our main sequence stars data, because we were originally working with our data on Google Sheets, but we found more success after pivoting to Excel. And additionally, our data did not turn out as we expected, as we mentioned some of our errors and ways we tried to fix those earlier. But at the end of the day, science may not always turn out as we expect it to, because it's all about trial and error and the process of investigating for new discoveries.
And so reflecting on the Seye's experience as a whole, Seye's has been an amazing, unique experience. I have learned what it's like to conduct authentic scientific research and how to work with others from around the nation to further our knowledge of space. Seye's has broadened my view of what is possible for me to achieve in post-secondary education.
Participating in NASA Seye's program was a transformative experience that significantly heightened my appreciation for space exploration.
Seye's has been an incredible opportunity for me to do unique scientific research and add to the body of knowledge regarding astronomy and open clusters. Seye's has shown me what it's like to do research in a group, and it has also expanded my interest for my secondary education.
Seye's has provided me with an amazing opportunity to experience what space science is all about. Being able to conduct hands-on research with a team of peers has provided me with a memorable and valuable experience of how fun and challenging research can be.
NASA Seas has given me an invaluable opportunity to explore the evolving field of space science. I've enjoyed working with driven peers, gaining important research skills, and broadening my perspective on space research into my future education.
Participating in SEAS has enabled me to engage in scientific research within astronomy for the first time. Through the program, I've collaborated with talented peers from across the country, exposing me to new ways of thinking, techniques, and this fascinating field.
Working in SEAS has taught me many new concepts in such a short time, drawing my interest into various fields of astronomy. It was incredible to participate with a great group of high schoolers, solving problems and finding unique solutions.
These are the references.
We would like to extend our heartfelt thanks to Dr. Olivia Kuper, Mr. Thomas Rutherford, the Southeastern Association for Research in Astronomy, NASA SEAS, UT Austin, and the Center for Space Research. Thank you.